much, and thanks a lot for the invitation. I'm sorry that I couldn't be here in person. I hope the snow is good. So yes, so what I'm going to tell you about, I'm going to start by telling you two, or reminding you rather, two well-known stories. So one is the construction of a quantum group from the clinician examological of equations, and this is a very old story. And another, slightly more recent, but still at this point not super recent, is a construction by Phil Bolch of the semi-classical limit of the quantum group, namely the Poisson Lie group, the dual Poisson Lie group G star from Stokes phenomena. And then I want to explain two things. I want to explain how you can revisit this construction of the quantum group to give purely and entirely transcendental construction of the quantum group. So this is a paper of mine from 6 years ago. And then I want to now relate this revisited construction of the quantum group to Phil's construction of the dual Poisson Lie group in a precise way. And I want to explain that Phil's construction of G star is a semi-classical limit of the transcendental construction of UH bar G that I'll explain. And this part is joint with Xiaomeng Xu, and it's on the archive. In fact, it appeared this morning on the archive. All right, so let's start from the beginning. So let me quickly remind you how you construct the quantum group from the Case equations. So the first step, I'm going to go here a little quickly because this is probably known to all of you, but feel free to stop me. So we start from the Case equations in 3 points, which are this equation here. This is equation with values in the third tensor power of the enveloping algebra. And these omega ij's are Casimir tensors. And then this equation has a parallel transport, rather regularized parallel transport from 0 to 1. And what this is an element of, this is a formal power series in H bar with values in the third tensor power of UG. And H bar here is 2 pi I times this complex parameter H. So the first step in the construction of the quantum group is to so to speak, follow the science. So you want to relate the Case, you want to understand the Case equation. So what are those Case equations? And so the statement is that once you take the enveloping algebra, its standard tensor product, and you put in this Case associator and the monodromy of the Case equations in 2 points, then this is a braided tensor category. Moreover, it's a useful braided tensor category because it produces, therefore, for you lots of braid group representations. And what these are is no more and no less than the monodromies of all Case equations in an arbitrary number of points. Right? So you've been able to sort of compactly package all these monodromies into the statement that this short list here is a braided tensor category. Equivalently, perhaps a little bit more technically, you could say the following. If you don't want to speak about categories, you could say that you're going to take the enveloping algebra with trivially deformed coefficients, its standard coproduct, this monodromy of the Case equations in 2 points, and the associator. And then what this is technically is a quasi-triangular quasi-Hopf algebra. And the second quasi, as in quasi-Hopf, refers to the fact that you should think of the standard coproduct as not being quite co-associative, meaning that if you take a threefold coproduct, namely this, it's the same as the other threefold coproduct. So each of these corresponds to some bracketing. So this one would correspond to like so, and this one in the middle corresponds to this bracketing here, right? And these two, you shouldn't think of them as equal, but rather you should think of them as related, as conjugate to each other, and the conjugation constant is exactly the associator. Okay, so we want to get to the quantum group, and the first step has delivered something which isn't quite the quantum group, because because it's a quasi Hopf algebra. So it has this associator, and we want to get rid of it now. So the second step is to say that in categorical terms, you would look for a tensor structure on the functor. So there's a forgetful functor from this category I introduced, this Drinfeld category here. There's a tensor functor to vector spaces, which is just the forgetful functor. Sorry, there's a forgetful functor to vector spaces, but it's not tensor a priori because of this non-trivial associativity constraint. So you want to find a tensor structure on it. Equivalently, in algebraic terms, this means that you look for a twist, which is the same, that's an element in the second tensor power of G, which kills this associator. So killing this associator is this identity here. So I'm not going to spend too much time on it, but what this identity implies is that if I then take the very same enveloping algebra here, but now instead of taking the usual coproduct, I'm going to conjugate it by this element here, this twist. And then I'm also going to conjugate this the monodromy on 2 points by J, or a twisted version of J. And then the claim is that this is an actual Hopf algebra. So it's no more quasi Hopf. And to prove that such a twist exists, so there's several proofs available. Drinfeld's original proof was a cohomological argument, so it was not constructive. Kashdan and Lustig later gave a constructive proof using what you might call Verma tensor yoga. And then Pavletnikov and Kashdan later enormously generalized this proof and made it work for an arbitrary Lie algebra. Okay, so now this is a second of 3 steps. So we had a quasi-Hopf algebra. Now we have a Hopf algebra. Now we want to convince ourselves that we've gotten the quantum group we wanted in the first place. So how do you show that this is the quantum group that we wanted? So Drinfeld gives, again, a cohomological proof of this. Kashdan Lustig gave a constructive proof by very hard algebra. And then Ettinghoff and Kashdan gave also constructive proof by a much softer algebra, so much more pleasant algebra. Okay. Right, so this is it. And I just want to comment that in some sense, it's clear that the associator comes from the K's equations. But in some sense, it's not really clear that this twist that's constructed either here, here, or here comes from the K's equations, in the sense that it's obtained by an algebraic procedure. And in fact, as Ettinghoff and Kashdan showed, that procedure, which they devised, works for an arbitrary associator, in fact, over an arbitrary field of characteristic 0. So you're not really exploiting the K's equations at points. So you use them to get the K's equations, then somehow you throw them out, and then go into characteristic 0 arbitrary associator land. Okay, so the first thing I want to explain is that you can actually construct a twist directly from, yeah.
A question, possibly slightly tangential also. Hi, this is Tudor. So this this construction that you described relies on sort of starting with a Lie algebra at the beginning.
Yes.
Is there any generalization that would take as input a VOA and the KZ connection that comes from the stress tensor and spit out something close to a quantum group?
I think Paschal is the person to ask, but of course that seems tricky, because I mean, obviously you will have a braided tensor category. The question is, can you construct a tensor functor to vector spaces?
Right.
In fact, I suspect there may actually be there may be counterexamples to this, but Pavel is the world expert on tensor categories, so maybe he should chime in here.
Sorry, that was tangential. Thank you.
So where was I? Yes, I was saying that what I want to explain is to construct a twist or a tensor structure, but staying within the realm of K's equations. And you might say, why do you want to do that? Because what I'm going to explain now only works over the complex numbers and only ever works for the KZ associator. Nothing. I can't do anything over Q, and I certainly can't do anything with an arbitrary associator. So one is a kind of maybe stylistic motivation. You want to stay with the KZ equations throughout. So, but maybe a bit more seriously, this construction that I will explain is a key ingredient in showing a different result, which is that the monodromy of another connection, namely the Casimir equations for G, is given by the quantum Wahl group operators of this quantum group. So for that, to prove that, so this is something I proved some years ago, you need a kind of better comparison of the quantum group and the enveloping algebra. And this better comparison comes from this purely transcendental twist. Okay, so the main ingredient, as already advertised, are the case equations, but the case equations with a little twist. And this is a twist that was introduced originally by Giovanni Felder, Markov, Tarasov, and Varshenko. And here I'm giving you just the case equations in 2 points, but there are such equations for an arbitrary number of points. And so in 2 points, the case equations would be the regular case equations would be just this. So forget this term, right? And now we're adding a so-called dynamical term, which is, so I'm fixing a point in the Cartan, and I'm letting it act on the first tensor copy. So these case equations are valued in UG tensor UG. Okay, so I've added this mild term here. Okay. And I have to say that I have some idea why Giovanni and collaborators introduced this dynamical term, but it took me a very long time to understand what this term and so what it was good for. But it turns out it's extremely useful. So as I'm going to explain next. So let's talk about this equation, and I want to construct two fundamental solutions for it. So the first one is something that you would also construct for the standard case equation, so the ones you would get by if you deleted this dynamical term. And so at this point there's a regular singularity, so it's a general result that there's a solution which has a holomorphic part, and then this singular part, which is z to the h bar omega. I guess my h has become h bar now, but okay, and so so this is a completely standard result. Now we go to z is equal to infinity, and at z is equal to infinity, this term mu1 introduces an irregular singularity. So you might first think that this makes life much more complicated, and in fact it does technically, but conceptually it makes it much simpler, because so now I'm going to assume that my mu is a regular element in the Cartan, which is it's a standard assumption in these kinds of differential equations. Let me try to keep the differential equation on the screen if I can. I'm going to denote by omega 0 the Cartan part of omega, so that's the projection of that, and then it's standard. I mean, it's not so difficult to prove that there is a formal series in UG tensor UG with coefficients in Z inverse. So it's a formal expansion at Z is equal to infinity, normalized by the fact that it at infinity is equal to 1, such that this formal solution, which is h infinity times e to the z mu, and then the term you had here, which was z to the h omega, which was near 0, has now been compressed to z to the h omega 0. So you're only left with the abelian part of this Casimir tensor. Okay. Now the problem with this solution, which is standard from irregular singularities, is that the radius of convergence of this formal holomorphic part, this formal power series, is equal to 0. Now, if this equation were to take value in a finite dimensional vector space, then there would be a way to resum this formal power series to get honest holomorphic functions on half planes, so planes of aperture pi, for all but finally many directions. Now, in this case, the dynamical case equations take value in this infinite dimensional vector space, and there's Stokes rays, and these Stokes rays can be there's infinitely many, and if you don't make your choices right, there's densely many. So it makes life. So I'm going to make now a further assumption, which you wouldn't think to do for ordinary ODEs, which I'm going to further assume that my mu is a real point in the Cartan. So at this point, mu regular here, and now it's real, so mu is constrained to live in a chamber. And that simplifies life, because then now the Stokes rays are all in the positive or negative direction of the real axis. And the theorem now, which I proved some years ago, is that H that we discuss here can be resummed. So there are two honest solutions. Honest means that they're holomorphic in the upper and the lower half planes, and they have the asymptotic behavior that you would expect from the theory of ordinary differential equations. Okay. So once I have those, and now remember I had a solution, a standard solution near zero, and now I have two slightly less standard solutions near infinity, one for positive half plane and one for the negative half plane. And I'm now going to introduce the fusion operator, which is just basically the constant, so to speak, the constant element of UG tensor 2 that relates them, right? So they differ by constant element, and this is the constant element, which is still a function of mu. And the claim is that when I look at it, so this is an element in UG tensor 2, and the claim is that this is a twist which kills the KZ associator. Okay, so if you believe this, then you see that by starting from the KZ equations, or rather their dynamical versions, in merely 2 points, you construct an object which actually gives you a twist, or equivalently a tensor functor from this Drinfeld category to vector spaces. And the added bonus, which would be maybe not so relevant for us today, but let me mention it in passing, is that you remember this everything depends on this parameter mu which we inserted, which lies in a chamber. And the added bonus is that this twist or fusion operator is a smooth function of that parameter. So it's a C infinity function. And if you differentiate it, it satisfies a version of the Casimir equations of the Lie algebra. So it satisfies this equation here. Okay. All right. So maybe any questions at this point? No. Okay.
Sure. Hold on.
Yeah.
So this is the connection matrix between zero, the tame
Exactly.
points, and the different
Yes.
sectors. So is this like a quantum version of this, like Duality map twist, which was the way to go between the the diagonal part map and this Iwasawa projection? Is that like a good way to think of it, or?
So you've already half stolen my punchline, but I think
I'm sorry.
but that's fine. That's fine. I think the answer is very likely yes. So the fact that this is a connection matrix will become very important in a little while. So yes, and I'm actually not so familiar with this Duality twist that you mentioned. So maybe you can tell me more about it. But I suspect that very strongly yes.
Okay.
Any other questions? No. Okay. So let me make a few comments. So the first one I've made, so that the existence of these solutions is standard, but for infinite dimensional coefficients, it requires more work. The second is, once you've got that, you would say, oh, but are you sure that you got the quantum group this way? And the answer is yes. So this universal enveloping algebra with this twisted coproduct and twisted R matrix is isomorphic to the quantum group. And you can give two proofs of that. The first one, there's a general result of Drinfeld that says that Drinfeld uniqueness says it has to be somehow, but that it's not a constructive isomorphism. And then in collaboration with Andrea Apple, we're actually working out an explicit isomorphism of this twisted enveloping algebra with the Drinfeld-Jimbo quantum group. And to close this part, I just want to mention that both these theorems, so the construction of this fusion operator, and the identification with the Drinfeld-Jimbo quantum group, generalized to an arbitrary Kac-Moody algebra. This statement has to be corrected a little bit, and as does the description of quantum Wahl group operators in terms of the Casimir equation. And so this is work that I've done with Andrea Apple, which is on the archive. All right, so this was the quantum part of the story. And now I'm going to just briefly review the classical part of the story, or the semi-classical part of the story, which was worked out by Phil. So so what do we do? So Phil starts with this differential equation. So df over dz is a over z squared plus b over z f. Now b is an arbitrary element of the Lie algebra, and a is in the Cartan, is also a regular matrix. And I'm going to make an assumption which Phil does not do, but this is simply to simplify the exposition. I'm also going to assume that this is real. So when I did it earlier, I needed to do that. Here, this is simply just to shortcut the exposition. Now, under these assumptions, in fact, I don't. There is a unique fundamental solution which is holomorphic. There's one on the upper half plane and one on the lower half plane, which has the asymptotic behavior that that phi goes like e to the minus a over z times z to b, and bracket b is the projection of b onto the Cartan as z tends to 0. Okay. And once we have these two solutions, we can define the Stokes matrices of this connection as follows. So I have phi minus, which I think of as rooted in the lower half plane. I can continue it half a turn to the upper half plane, and then compare to the solution which is rooted in the upper half plane, which is phi plus. And those two are going to differ by a constant matrix, which I'm going to denote by S plus. And likewise, I can take phi plus and I can do a half turn of that. So I analytically continue it counterclockwise to phi minus. And so it's going to differ by a constant. But here I did something which I didn't do here, which I also crossed the log cut. And so I'm going to add a factor of e to the 2 pi I diagonal part of b to correct for that. And so these Stokes matrices S plus and minus, you can think of them as half monodromies, in the sense that if I were to compute the full monodromy around 0 in the fundamental solution phi minus, well, I can compute it in two stages. I can compute first and second like this. The first step would give me S plus, and the second step would give me this. So the product of these Stokes matrices with this phase factor in the middle gives me the full monodromy. But they are per se a finer invariant. So remembering this factorization as S plus and S minus times this is a finer invariant, and it's the right thing to do in this case. Also, it's a well-known fact from ODEs that Stokes matrices are unipotent, and more specifically, in fact, they lie in the unipotent groups whose subalgebras are the algebras of positive and negative root vectors for the corresponding to the chamber where my A lies. Okay, so this is Stokes matrices, and now what does Phil prove? So he assembles these Stokes matrices into a so-called Stokes map. So I'm going to identify G star with G, and then I'm going to take a B. That was my coefficient matrix here. Okay, and from B, I'm going to take essentially the Stokes matrices. I'm going to take S plus and S minus, but for various reasons, I'm going to take S plus inverse and then put half a phase factor here, and then S minus with the other half of the phase factor here. And at this point, this is an element in the fiber product of the positive Borel times the negative Borel over H. And this is as is probably known to all of you, this is the Poisson Lie group that's dual to G. And so what Phil proves is this remarkable result that this map, once we identify G and G star, this map is a Poisson map, and he also proves that it's actually a local analytic diffeomorphism. So you can think of this result as a linearization result for the Poisson Lie group G. So locally, this Poisson Lie group G looks like the flat Poisson Lie group G star with its standard constant Kirillov-Suryo Poisson structure. And such results have, there's a bunch of very beautiful results along those lines. It was first proved by Ginsburg and Weinstein, but in a cohomological non-constructive way. Then Anton Alexeyev and Ecker-Manrenken gave a proof for the unitary groups. Then Enriquez, Ettinghoff, and Marshall gave a proof in a formal setting. I'll return actually to one of the ingredients in their proof. And then again, Alexeyev and Manrenken proved in 16 an analytic version of this linearization result, which works for it's an honest analytic linearization, and it works for co-boundary Lie groups. So in any case, there's a bunch of ways to linearize this. And I particularly like this one because it uses Stokes data, and that's the one that I'm going to be to relate to in what I say next. But maybe I should ask if there are any questions at this point. So we covered the quantum story. This is construction of the quantum group via the dynamical case equations, and now Field's construction of the dual Poisson Lie group using Stokes data. Any questions? No? Okay. All right. So now I want to tell you about my work with Xiaomeng. So everything I'm going to say from now on is joint with Xiaomeng. And so the slogan that I want to explain is that this construction of G star is, in a precise sense, is a semi-classical limit of the transcendental construction of the quantum group that I explained. And a slightly more precise corollary of this vague slogan is, for example, that the Stokes map that Phil introduced can be quantized actually canonically, although in a formal setting. In particular, the fact that it possesses a canonical quantization gives an alternative proof of the fact that it is a Poisson map. And so I want to explain. So Xiaomeng do somewhat more than this, but I want to use this corollary as a kind of as an excuse to tell you the proof of this corollary as an excuse to sort of guide you through some of the things that we do. So what do we do? So we want to prove this. So what is the strategy? The strategy is we want to quantize everything. So to do that, but we are going to do this in a formal setting. So I'm going to look at G star as this linear Poisson manifold, and I'm going to replace it with the ring of functions on the underlying formal Lie group. That means I'm just going to take formal power series on G star. Similarly, I'm going to replace the honest Poisson Lie group G star by the ring of formal functions on it, so which is by definition the formal Poisson Lie group underlying G star. I'm also going to take a formal version of S. So I'm going to replace S by S hat, which is its formal Taylor series at 0. And so if you wonder what this is a formal Taylor series on G star, right? This G star is where B lives, that coefficient B, with coefficients in the dual Poisson Lie group. And this plus is something that Joel yesterday in his talk was denoting by 1. It's saying that the value of this formal power series at 0 is equal to 1. So this is a pro-unipotent group. Okay. And further, rather than this formal Taylor series, I'm going to look at its pullback. So its pullback is then a map from formal functions on capital G star to formal functions on Gothic G star. Okay. And note that because the original Stokes map is holomorphic, it's going to be Poisson if and only if its formal power series is Poisson, and therefore if and only if this Poisson, this pullback is a formal Poisson morphism. So I can now free myself completely from the analysis, so to speak, and go into this world. And if all I'm interested in is to say that this map is Poisson, well, this formal world will suffice to that end. Okay. So where we are is here. We've now formalized everything. And then what I want is to quantize this. So that means that I'm going to replace each of these algebras by an appropriate, of each of these Poisson algebras by an appropriate quantization. So I'm going to quantize this into that. I'm going to quantize this into that, which quantizations I will explain in a moment. And then I want to find an algebra isomorphism between these things, which I'll call S hat star H bar. And then finally, I'll want to say that this thing here is a quantization that, in other words, that this diagram commutes where the vertical arrows are simply specialization at H bar is equal to 0. Okay, so let me first tell you how you do this and that. So how do you quantize these formal Poisson Lie groups? So there's a very known result of Drinfeld, which is called Drinfeld duality, and works as follows. Suppose I start with a Lie group P, and I start with a QUE, so a quantized enveloping algebra. What is that? This is a Hopf algebra over the ring of formal power series, such that when I specialize it to H bar is equal to 0, I get the enveloping algebra of my Lie group P. Okay. So there, by definition, I therefore have a specialization map from this bold-faced U to this universal enveloping algebra. But there is another and slightly subtler specialization where I can take a different limit of this and get myself into a commutative algebra, a commutative hop algebra, as opposed to something which is non-commutative, which turns out to be exactly the algebra of functions on this formal Poisson Lie group. And so it goes like this. So let me tell you some of the steps. So if I have this QUE, then it induces a Poisson co-bracket on the enveloping algebra simply by taking an element, you take its quantum coproduct, then minus its opposite quantum coproduct and divide by h bar. This is divisible because I have this specialization here, and therefore I can evaluate it. So this is the same way as you would define a Poisson bracket from a non-commutative deformation of an algebra. And now I have the Lie algebra P, the standard bracket, I have this Poisson co-bracket, and this is a Lie algebra. And I can take its transpose, so I can take the dual vector space, the transpose co-bracket, which is now bracket, and the transpose co-bracket, which is now bracket, and this is also Lie algebra. And P star, by definition, is the Poisson Lie group, which has this Lie algebra here. Okay, now what Drinfeld stated without proof, and then Gavarini filled in the details, is that this QUE, admits a canonical Hopf subalgebra called U prime, which is, unlike U, is commutative mod H. So U is co-commutative mod H. This U prime is commutative mod H. And when you specialize it to H bar is equal to 0, you get functions on this formal Poisson Lie group, P star. And when I say you get, it's not exactly on the nose. There's a rather non-trivial isomorphism between these two. And this was somehow only appeared later in a paper of Enriquez. I've given you the formula here. We're not going to use it as such, but I just want you to remember that this identification is by no means trivial. It's given by a somewhat involved formula. All right. So this is Drinfeld duality. So Drinfeld duality is a device to give formal quantizations of Poisson Lie groups. So let's do a first example and see how that works. So I have a Poisson Lie group which is G star with its constant Poisson bracket, and I want to give a formal quantization of that. Of course, we all know one, but let's see what Drinfeld produces in this case. So you could start from the trivial deformation of the enveloping algebra. So I just extend the coefficients. The product is untouched, and the coproduct is the co-commutative one. The underlying Lie algebra is of course going to be G as a Lie algebra, and then the co-bracket you get, because this was co-commutative on the nose, is the trivial co-bracket. So when I dualize, I then get G star with a trivial bracket and a non-trivial co-bracket, namely the transpose of the bracket on G. And the corresponding Poisson Lie group is G star as an abelian group, and then with the Kirillov constant Suryo Poisson structure. Now, what does U prime turn out to be in this case? It turns out to be the vector space of formal power series, where with values in UG, where the coefficient of h bar to the n, this xn here, has order in the PBW filtration at most n. So another way to say this is that this is the enveloping algebra of G, but with brackets scaled by h bar. Or another way to say is that this is nothing but the Riesz algebra of UG with respect to its standard filtration, or rather the completed Riesz algebra of UG with respect to that filtration. Okay. So once you've made this very easy observation, then you know that when you set h bar to 0, that means you're taking the graded. So this graded, because of the completion, is the direct product of all symmetric algebras, and this by definition is clearly functions on G star. And what is this, what I termed as a complicated identification between this quotient and this? In this case, it's nothing but the symbol map. So in this very special case, the identification is just a standard identification you'd think of writing. Okay, so this way we've used now, somewhat underused, if you will, but we've underused a Drinfeld duality to give a formal quantization of G star. Now I want to use Drinfeld duality again to give you a formal quantization of the dual Poisson Lie group, capital G star. Now for that, the natural temptation is, why don't I start with the Drinfeld-Jimbo quantum group? After all, this is a QUE which deforms the correct Lie algebra structure. So let's start with there, and then Drinfeld duality will tell me that if I specialize it to 0, there is some identification with functions on the dual Poisson Lie group. But what I want to contend is that for our purposes, which you remember we had here a quantization diagram we're trying to compute. So we've checked that box. If we take the Drinfeld-Jimbo quantum group, we've also checked that box. But the next step is we want to establish that there is a map between those two things, right? And for that purpose, this starting from the actual Drinfeld-Jimbo quantum group is not very useful, because you have to produce such an isomorphism, and then you have to complete the final step, which you have to show that it induces the Stokes map. And those are very difficult things to do with this Drinfeld-Jimbo quantum group. So we're going to take another candidate for this quantization. And so we're going to do a take two of this example. So to obtain a formal quantization of G, we're still going to use Drinfeld duality. But instead, we're going to start from a preferred quantization, which is to say something which as an algebra is equal, not just isomorphic, it's equal to the trivially deformed enveloping algebra. But we're now going to twist the coproduct with the twist that I constructed from the dynamical case equations. So this is a quantization, and so it's going to give us a formal, by Drinfeld duality, a formal quantization of this. Okay. So where are we now? So we've now ticked this box. So we have a formal quantization of this. We have a formal quantization of functions on this dual Poisson Lie group. And now we look for this isomorphism here. Okay. And now we're going to resort to a general result of Enriquez and Albu, which says that take a twist which need not come from the dynamical case equations. Just take an arbitrary twist, J, which kills an associator, and we assume a technical condition of it, which is that it should be admissible. So this means it's a condition on the growth of on the filtration growth of its coefficients. Then, and maybe I should put some parentheses here. Then the claim is that two algebras coincide. So the left-hand side was the trivially extended, was this completed Riesz algebra, right? And on the right-hand side was Uj is as an algebra, just U, the enveloping algebra with trivially extended coefficient. But when we take the prime, we have to take this Drinfeld subalgebra, and the definition of this Drinfeld subalgebra very much depends on the coproduct. And the coproduct here is twisted by the twist. So you expect that the right-hand side very much depends on the twist. And Enriquez and Albu tell you that this is actually not the case. That is, so long as the twist is admissible, then those two algebras are actually the same. So it's a non-trivial result. It's an estimation of growth of coefficients of these things, but it's true. So as a corollary, provided you prove that this dynamical KZ twist is admissible, which is not difficult to do, then we're almost home, because we've quantized functions on G star, we quantized function on capital G star. We now have an isomorphism, which is, I'm denoting by E, but this is just equality now because of this result here. And now the last thing to do is we want to check that this is a commutative diagram. And so how do we do that? Well, for that we need a further result, which we would like a formula for this composition here. So we would like a formula for what I'm calling E classical J. So E classical J is the specialization of equality at H bar is equal to 0, which of course is still equality. But then we compose it with this complicated identification here, the inverse of it to go up, and then with the symbol identification here, E0. Okay, so this is the semi-classical limit of this equality, but after I've identified things the way this is not an E0, this is an I0. And there's a theorem due to Enriquez, Ettinghoff, and Marshall that gives an explicit formula for this map here, or better, for its composition with the big cell map. So the big cell map is a map from G star to G, which takes these two elements, B plus and B minus, and multiplies B plus on the right by the inverse of B minus. So we're going to look at it as a formal map, this big cell map, but and it becomes an isomorphism at that point. So it's a formal map from G star to G. And what this result that I'm going to say in a second gives you is an explicit formula for this composition. And so we're going to make some additional technical assumptions on the twist. So we're going to say that J is in U tensor U prime intersect U prime tensor U, and that phi is a Lie associator, which is certainly the case for the KZ associator. So J for now is not necessarily the dynamical KZ twist. So now we're going to consider this quotient U tensor U prime over H bar of it, which I can think of, if I think of the H bar as living here, I can think of this as formal power series on G star, because if I take U prime over H bar U prime, that gives me the completed algebra of G. So that's functions on G star with values in UG. Okay. Inside this algebra formal power series, I can find the pro-unipotent group, which arose earlier, which is the pro-unipotent group of formal power series on G star with values in G. And this is actually, in fact, is exactly the algebra of the group of group-like elements in here. And given such a twist J, I can look at its semi-classical limit, which I'm calling lower script J, lowercase j. And by definition, this is J modulo this H bar U tensor U prime. So this is how I'm taking, by definition, how I'm taking semi-classical limits. And so then this theorem asserts two things. First of all, this J, which in principle just lies in here, it's just a formal power series of value in UG, actually is a group-like element. In other words, we can think of it as a formal map from G star to G. Okay. And secondly, when this composition of this classical limit with the big cell map here is a twisted conjugation. So it's a twisted exponential map, which is to say that it's a formal map from G star to G. And what is this formal map given by? I first take an exponential, and before taking the exponential, I go from G star to G using the inner product. Then I take this exponential, and then I conjugate my exponential by the inverse of J of lambda. Okay, so this is a twisted exponential map, and Alexeyev and Meinrich made extensive use of these twisted exponential maps to linearize co-boundary Lie groups. Okay, so we have this very nice formula, and this is the one I'm going to use now to show you that if I take J to be this J to be the differential KZ twist, then I get exactly a commutative diagram. So what I want to show you is that I want to show you that this classical equality descends to the Stokes map, but it's the same test to do that when I compose with the big cell map. Now, so let's compare these two. Now the left-hand side is this by this formula of the EEM that I just explained. And now what is the Stokes map composed with the big cell map? Well, by definition, it's just S plus e to the 2 pi I diagonal part of B S minus. That's just by definition of the Stokes map, which, as we've already discussed, this composition is nothing but the full monodromy in the solution phi minus around 0, and then inverted. Now, there's a different way to compute this monodromy, which is rather than think of it as doing a small loop around 0, I could do a big walk to infinity, then take a small loop around infinity, and then do the inverse of that big walk. And so I can think of this monodromy as conjugated to e to the 2 pi IB, which is the full monodromy around infinity, by a connection matrix CR. So this is which is what Phil was alluding to earlier. So the CR is the constant element of G that relates the I got my notations wrong, sorry. Which relates phi minus to the canonical fundamental solution at infinity. Okay. And so therefore, to prove that the classical, that that S hat is quantized by that equality up there, all I need to show is that I have to have the equality. I mean, I'm comparing this and that. So I have to compare, I have to show that this connection matrix is J lambda inverse. So I have to show that this connection matrix is the semi-classical limit of this twist that I constructed from the dynamical case equations. Okay, so it's I'm just comparing two things and using this monodromy relation here. And so how does that follow? So, I mean, in a word, it follows because this twist by construction comes from the dynamical plane. On the other hand, this connection matrix arises from the differential equation that Phil has been considering. And the basic observation that Xiaomeng and I started from is that the differential equation that Phil studies is in fact exactly the semi-classical limit of the dynamical case equation. I mean, on the nose. So I just want, this is a very simple observation. So I just want to, but it's very basic, but extremely useful observation. So I just want to explain that. So let's think of taking the semi-classical limit of this differential equation here. So the main thing is to take the semi-classical limit of this h omega. No, h omega is this thing here. And I'm going to introduce h bar, which remember was h times 2 pi I. Take the classical limit, essentially this h bar goes away. And so I'm finding the same expression, except now the first leg, I'm still thinking in terms of UG. And the second leg, I'm thinking as an element of SG, or rather better, maybe G. And so the semi-classical limit of h omega is a function from, not even a formal function, from G star to G, which takes a lambda and maps it to nu lambda, where nu lambda was the usual identification between G and G star given by the inner product. So then if I take the semi-classical limit of all of this, well, it's easy to see that I just get d minus mu plus 1 to pi I nu lambda dz. And this, I now contend, is exactly the differential equation that Phil uses, provided you make a change of variable. So you want to send z to 1 over z, so that, because this has an irregular singularity at, I think I'm missing a coefficient here. This is here, should be here, right? So this is an irregular singularity at infinity, and this is an irregular singularity at 0. So you want to do this small change of variable, and then you want to identify A with minus mu, and then B with minus mu lambda, 1 over 2 pi I. But once you do that, one is exactly the semi-classical limit of the other. And so then it gives you the hope that such a thing will be true of all the package that comes from the differential equation. It's canonical fundamental solution, it's monodromy data, and so on and so forth. And as it turns out, it's true. This is the main technical result that Xiaomeng and I prove, although it requires, of course, some work. And so the main technical result is that once you make these changes of variables, which I've already mentioned, then the canonical fundamental solutions of the dynamical case equations, which I constructed, so there was 1 at infinity and 1 at 0 and 2 at infinity. First of all, they lie in U tensor U prime, so you can take their semi-classical limit. And then once you do, you find that they are the same as the canonical fundamental solutions of this differential equation here. And in fact, rather to say that they are those, they're rather the formal Taylor series of these solutions viewed as functions of B. And then once you prove that, then the same applies to all the monodromy data. So the Stokes matrices, the connection matrices, and so on and so forth. And this is the main result that you then need to be able to link. So this is the sense in which the dynamical case equation descends with all its stuff, all its baggage of solutions, monodromy data to this differential equation with its own monodromy baggage, and then therefore that allows you to conclude that you have quantized the Stokes map. Okay, so I guess I ran a little early, but I'm done.
Thank you. Merci. Questions?
Right. So I have a question about just this second to last page, page 16, where you took the semi-classical limit of the dynamical KZ to get back this meromorphic connection with the pole over 2 at infinity. So when I take the semi-classical limit, I'm used to see like the semi-classical limit of that as giving not the meromorphic connection, but rather the isomonodromy connection for those meromorphic connections there. I don't know if I'm making this clear. For instance, if mu is...
Mm-hmm. Yes, yes. So the point is that this using the term semi-classical limit is sometimes a little confusing because it also always means you're modding out by h bar, but it depends what are you modding out by. So if you mean what I was doing, which is modding out by u tensor u prime, this is what you get. But it is also true that under this, and I know I kind of chose not to explain this, but I remember I told you that there is this Casimir connection for G. And then this Casimir connection for G under the same semi-classical limit becomes a non-linear connection, actually, once you descend it. We also explained that in our paper with Xiaomeng. And that becomes the isomonodromy equation that Phil, that Jimbo Miwa Ueno wrote down for GLN, and then Phil generalized for an arbitrary semi-simple Lie group.
Okay, so is somehow...
Yeah.
Sorry, just a follow up, but I mean, I think I see. So is it somehow the trick that the semi-classical limit of omega of the canonical tensor here is not the quadratic stuff, but what you're getting is only an element in G rather than G tensor G, right? That's the only difference I see.
Yes, that's the only catch. So you would think, so you would think that the quadratic tensor should descend to something quadratic. And in fact,
right,
because of the way we're doing it, and we're only taking, so to speak, limit in one leg, which is the second one, it becomes quadratic, but it's a map. So it becomes a map from G star to G, which is then linear, right? Which is actually the identity, or rather the inner product identification of those two.
Ah, I see. Okay. Oh, thank you. Okay.
So the B here, the B that you have here, you should think of this as B as a dummy. So it's a dummy variable. It's something waiting for you to give it your favorite B. So that B, you should think of this as a function, if you like, from maybe G to G, right? And likewise, the semi-classical limit of that is another function from G star to G, and those are the same once you identify G and G star appropriately.
Okay. Thank you.
Any other questions?
Yeah, so I wanted to point out this business with the exponential twists. It really is what Duality Map was doing, and so the Ginsburg-Weinstein paper was basically an extension of this 1984 paper of Duality Map about how to twist the exponential map to convert the diagonal part into the Iwasawa decomposition. And kind of what I discovered is that this connection matrix does give such a Duality Map twist. When you have a look at the skew Hermitian picture for compact groups, and so that's probably what's also appearing here.
Okay. All right, thank you. I guess I learned about this twisted conjugation in the paper of Alexeyev and Meinrich, and maybe I overlooked it in yours. So okay, thank you. So I'll look it up. But yeah, very likely this is what's happening.
Is there hope to do something which is not quite so formal, that maybe analytic or a slightly bigger open patch than the completion at the identity or at zero?
Yes and no. So for the particular purpose of what I explained, I think you agree that you can get away with formal because all you need is basically the jet of the Stokes map, right? At zero, right? So if you want, all you want to do is that it's Poisson, that's all you need, right? But that's not.
If you have an analytic.
If you have an
analytic map, I want to prove it's Poisson, but obviously if you prove it's formal without having proved it's analytic to start off with.
Oh yeah. So it's not like and also the global properties you prove that it's it's locally, that those are, I think, are completely beyond the reach of any of the thing that I said today. I'm just specifically.
Yeah, I have this feeling that sort of more should be true quantumly, and it's not clear that.
So one thing, so this is part of what this project I mentioned with Andrea, that we're trying to construct an isomorphism from the quantum group we get to the Drinfeld-Jibbo quantum group. So this, you can do that in two flavors. You can do a kind of formal version, and then you can do a numerical version where the h bar is actually an honest number. And at the end of the day, that's actually what for example, Kazhdan and Lustig do. They actually, for them, h bar is an honest non-rational number, and I think we can do that too. So so we're certainly thinking about that too. And you're right that actually this Drinfeld duality actually exists. I only explained it in the formal setting, but Gavarini pushed it to the global setting. So there is a kind of sort of an honest, non-formal quantization of Poisson Lie groups, still using but then non-formal quantum groups. So it's not inconceivable. Yes, I think you're right. It's not. It could be that you can actually just send to the numerical setting and then give quantizations of honest things rather than formal ones.
Have you looked at these papers of like Christian Kassel and Chureyev, where they try to look at both of these deformations in one package at the same time?
I am aware of it, and I think I had looked at them way back when. I somehow never.
I mean, does that help at all, or is it sort of? Yeah.
It's a good question. I never thought to think about them in this context, but yeah, maybe there's something to think about.
I mean, I looked at it a bit, and just they don't give particular examples, and so I got stuck just trying to work out basic examples. But I imagine experts like you would know, what's actually happening.
Right. So yeah, just remember this. They said they have a hybrid thing that specializes both to G and to G star, right? But yes, no. So I've never tried using them in this with this in this context. But it's another interesting suggestion actually.
Are there any more questions? No. Let's thank the speaker again.